I'm going to work through the 2019 HSC Option Topic 2 so you can see how to answer these questions. The first one is pretty straightforward. It's a binary addition and we need to show all the carry bits. The first one is pretty straightforward. 1 plus 1 plus 1 is 1 in the units column and 1 in the twos column. The next one is a little trickier. 1 plus 1 plus 1 plus 1 is 4 or 1, 0, 0. Now, we can do this two ways. We can either, well, we have to put the 0 there. We can either put 1, 0 here, and then the next addition will include a 1, 0, or what's cleverer is to jump across and put the 1 2 steps over. It doesn't actually matter. It doesn't affect the outcome at all. So 0 plus 1 plus 0 is 1. 1 plus 1 is 1, 0, and that's the answer. Okay, next question. Outline how the binary arithmetic processes of subtraction, division, and multiplication, 3 marks, 3 processes, can be achieved with a combination of adding, shifting, and flipping bits. Subtraction first. Find the 2's complement. By flipping all bits and adding 1. And add to the larger, not really the larger, the first number. Okay. Next one is, let's go to multiplication. Division is the most complex. So when we multiply, if you remember, 1, 1, 1, 0, 1, 0, 1, if there is a 1 in this section, then we draw it. If there's a 0, we don't. And for every place value we move over, we put 2 spaces or we shift over 2 spaces. So leave a space, and then 0, 1, 1, 1, and then add it all together. So there's my little example of how to do a multiplication. So by place value, and add all numbers together, and then we have division. So we have to do over and over again. We have to shift the divisor and subtract, and keep a tally of how many times we do that. So shift the divisor, divisor, and subtract repeatedly. Of how many times? Okay. Now, this one is a data representation question. So we're going to talk about how binary can represent different numbers. So let me redo that. 4 bytes can represent many different values depending on context. Okay, so if it's a string, then each byte represents a letter in ASCII. We can probably recognize A, 0, 1, 1, 0, 0, 0, 0, 1, represents lowercase a. And that's how these bytes could represent cat. I don't much like this question because this here is a dead byte if we're talking about cat. Like if you do the maths, that's the capital C, that's a lowercase a, that's lowercase t. So it can represent cat, but it means that you have to assume that that first letter is either a header character or a hidden character or something. It's just not very nice. I think they could have come up with something that was like a 4-letter word that was clearly representing a 4-letter word. Anyway, continuing. If they represent an integer, then it's a big integer. We know that 2 to the 10 equals 1024. We've talked about that a lot. So 2 to the 20 is approximately 1 million, and 2 to the 30 is approximately 1 billion. So that tells you that the number should be between 1 million and 1 billion. You do not have to do the maths. You're not allowed to bring a calculator in, so just sitting there and doing the maths is a massive waste of time. This is only worth 4 marks, and the 4 marks come from whether you can say that those are 3 different ways this could be represented, and if it shows a true understanding of what you're talking about. Okay, so a floating point number is represented with 1 sign bit and an exponent section and a mantissa. That's probably as detailed as you need to be. Okay. Okay, question D. Consider the following logic circuit. Draw a circuit that is logically equivalent to the circuit provided, but which uses the fewest number of gates possible. Support your answer with a relevant truth table. Okay, so we're going to need an original truth table, so we've got something to compare it to. So we're going to do that. A, B, we've got V, which is the equivalent, which is not A. I'll put that in brackets, V. And then we have W, which is not B. And then we have X, which is not A or B. So not A or B, and that's called X. And then we have not B or A before it gets passed through. So A or not B, which is Y. And then we have all of that added together, which is Z. And I'll write above it, which is A or B, not B, and not A or B. All of that added together gives us Z. Okay. We need 4 rows because there's 2 inputs. 0, 0, 0, 1, 1, 0, 1, 1. And not A is the opposite of A, so 1, 1, 0, 0. And not B is the opposite of B, so 1, 0, 1, 0. And not A or B is these two here. So when any of them is 1, the output is 1. So that's 1. 0 and 0 gives us a 0, and 1 and 0 gives us a 1. Now let's look at A and not B, which is this one and this one. So 0, 1 gives us a 1, 0, 0 gives us a 0, 1, any of the ones give us a 1. So that's what it looks like. And now we're ANDing together those two columns to find our output. So 1 and 1 is 1, 1 and 0 is 0, 0 and 1 is 0, 1 and 1 is 1. And you should recognize that that is the opposite of A, X, or B. Sorry, jam that in there, which is 0, 1, 1, 0. And so whenever we have the opposite of something, we can use the not equivalent of that gate. So the not equivalent of XOR is sometimes called XNOR, or also sometimes called not XOR. So A XNOR B, which looks like this: A, B, and then we have the XOR gate, which has a little circle at the end to show that it's a not, and that's the Z. That's our output. So now let's do our final truth table to show that the output is the same. A, B, Z, 0, 0, 0, 1, 1, 0, 1, 1. Okay, so A XOR B is 0, and not that is a 1. 0 and XOR 1 is a 1, not that gives us 0. 1 and 0 XOR'd gives us 1, and not that is a 0. And 1 XOR 1 gives us 0, and not that is a 1. So there's our output. That'll give you all the marks. Okay. And now we have the long question. So this is generally talking about a system and some kind of data stream. So here's our data stream. I'm going to assume that you can read this, and I'm just going to be responding to it. Okay, so question 1. A lot of processing. Okay. The drone has just moved to a position where it is 3 meters away from a wall to its left, 3 meters away from a wall to its right, and is 5 meters away from the wall in front of it. The nearest wall to the rear of the drone is 21 meters away. Okay, so we have a start bit. Construct a data stream that would be sent from the drone to the computer. Always has a start bit, so our start bit is 1. Then we have 4 bits, distance to the nearest wall to its left, measured in meters. So, sorry, the distance to the left is this one, 3 meters away from the left, which is 1, 1, but we must have 4 bits. So 0, 0, 1, 1, that's why we have these protocols, because otherwise the whole value would change. And then we have right, which is 3 meters away, which is 1, 1 again, so 0, 0, 1, 1. 5 meters away from the wall in front of it, which is 0, 1, 0, 1. And then distance from the nearest wall behind it, measured in meters, is 21 meters away, but there was a note that says if the distance is 15 meters or greater, or no wall is sensed, the value is set to 1111. So we're going to the maximum 15 meters, and then we must remember to put our stop bit in. And so that is our answer. I'll lay it out a little bit better so that you can see the bits, the parts clearly. So left, right, front, back, end bit. Okay, let's have a look at question 2. And we have a map. So let's have a look at this. The structure of the table data stream sent from the computer to the drone is shown in table 2. So we have to be able to interpret this table. The drone starts in the position shown in the diagram below. So here's our drone. The following communications occur between the drone and the computer. From the drone says 1, which is our start bit, 0, 0, 0, 1, which is a wall a meter to our left. Squares are 2 meters, so meter to our left, and then a meter to our right. No detected wall behind us, no detected wall in front of us, and that's it. And then from the computer says 1, which is our start bit, and then 1, which is motor on, and then 1, 1, which is forwards, and then 1, which is our stop bit. So it goes forward and ends up there. Okay, from the drone, start bit, then 0, 0, 1, 1, which is 3 meters. So 1, 2, 3, and 0, 0, 0, 1, which is here, and then 1, 1, 0, 1, which is in front of us. So 13 meters, so 1 to the wall, and then 2, 4, 6, 8, 10, 12, so that's here. And then we're back to the computer. So computer says turn motor on, and then go 1, 0, which is left. So it's going to travel left 2 meters and be here. Okay. From the drone, we have a wall 1 meter to our left and a wall 3 meters to our right. and a wall 3 meters behind us. Oh, sorry, silly me. 3 meters in front of us and 1 meter behind us. So 1 meter behind us is there, 3 meters in front of us is there, and then the computer hits it again and says go forward. So it goes forward and ends up here. And then we read from the computer again, which says I can see a wall 7 meters to my left. So 1, 3, 5, 7. And then 1 meter to our right, so that's there. And then 1 meter in front of us, we knew about that one. And then 3 meters behind us, we knew about that one. And that's it. Draw the movement of the drone showing all known walls. We did our thing. So that's the end of the unit. Sorry. I missed a question. Don't miss a question in the HSC. Explain the required changes to the drone and the data streams to enable the drone to explore a map of 3-dimensional maze. Okay, so this is not very tricky. Instead of going just forward, back, left, and right, we need to be able to go up and down. So we're going to need at least 6 different possibilities. At the moment, the computer only sends 2 bits to indicate direction. But to have 6 directions, 3 bits are needed. Whoops, needed. E.g. 001. I think 01 was left, wasn't it? Back is 00. Okay. 001 right. 010 left. 000 back. 011 forward. And then 100 up and 101 down. The data stream from, don't know where that B came from the drone would need to be longer. To give information about walls both up and down. So we've covered off the computer. We've covered off the data stream from the drone, but actually in order to pass that information, we're going to need more hardware. So go and have a look at the drone. Drone has 4 sensors and we now have 6 directions. So the drone would require 2 more sensors to about up and down. And that's it. And 3 things, look at that, 3 marks. Look, these things make sense. Okay, hope that was helpful.